In this video, I'm going to walk through just an example of using some of the binary tree code that's provided in the textbook. Now, note that there are different approaches you could use to programming binary trees with linked structure. So we're going to look at example code of using a linked implementation of a binary tree. That's different from the binary tree that uses an array like we looked at in the other videos. It uses a heap form array to store its entries like this. So this is one way to store a binary tree. Another is by using linked nodes. And I'm just going to walk through the code that does that linked implementation and just show you a quick example of how you could use those classes to create this particular tree that we've been looking at here. So there are two main classes that you're going to use. One is binary node and one is binary tree. So the binary node class, the instance data is a piece of data. So that's going to be the object that you're actually storing at that node in the tree. So in our tree example here, that piece of data will be a number, 4, 1, 2, whatever it is. And then there is a pointer to the left node and to the right node. So this is the basic implementation of a binary node. Instead of having, for example, our regular node class has a pointer to the next node, we have two pointers, one to the left child and one to the right child. This class gives three different ways to set up a node. You can set up a node as just null, so basically sending in no data. This would basically create an empty node. This constructor invokes the next overloaded constructor with null. So the second way to create a node is by specifying the data that will go in that node. And if you specify just the data, both the left and the right child nodes are null. So this would be a singleton node that doesn't have a left child or a right child. And then the third way to specify a node is by sending in the data and the node that is the left and right child. So three different ways to create a node with no data, with a data but no children, or with a data and two children. Then there's just some getters and setters. So there's a getter and setter for the data, getter and a setter for the left and right child. And then there are some helpful Boolean methods that return whether the node has a left or a right child. So if the left node is null, then this will return false, meaning this node does not have a left child. Same thing for the right. And also a Boolean method that returns whether or not this node is a leaf. Okay. There is a copy method, which allows you to create a copy of the node you're currently looking at. So if you want a second a second one of the current node, you can use the copy method. Then there is a method getHeight. So the getHeight method is going to return the height of the current node. So for example, the height of our root node is going to be 4. Sorry, root is 4 and the height is 4. The height of this node here, 1, would be 3, right? Because it's on, if this was the root of a tree, the height of that tree would be 3. So the height of 4 is 4, the height of 1 is 3, the height of 7 is 2, height of 6 is 1, for example. So in order to calculate the height of a node, what we do is we invoke the private and the private and recursive method called private getHeight, sending in a node. And in order, the node that we want to start with is this. So the current node you want to know the height of. So we say that the height is 0, and then assuming that the node is not null, the height of this current node is going to be 1. That accounts for the node itself, plus whichever subtree is taller. So the maximum of the height of the left child and the height of the right child. And then we just return the height. So for example, if we wanted to find the height of 3, we would say, okay, so the height of 3 is going to be 1 plus whichever is greater, the height of 2 or the height of 12. Well, so then we recursively find the height of 2. The height of 2 is going to be 1 plus whatever is greater, the height of 5 or the height of the right child. So then we try to find the height of 5. The height of 5 is going to be, if we're following our code along, whatever is 1 plus whatever is greater, the height of the left child and the right child. On that next recursive call, we would find out that both the left and the right child are null. So that would just return 0. So the max of 0 and 0 is 0. So the height of 5 is 1. That's going to then return up to the call we made with 2, which is going to say, well, which is taller, 1, or which is greater rather, 1, or the height of this non-existent subtree is 0. So that's going to be 1. So the height of 2 is 2. And then when we get up here to say the height of 3, it's going to be 1 plus the maximum of 2, which is the height of this subtree. and 1, which is the height of this subtree, and so the maximum is 2, so the height of 3 is 3. Okay, so that is our recursive getHeight method. Again, it recursively calls itself with the left and right subchild, taking the maximum value that's returned from those two recursive calls, adding on 1 to account for the current node, and then returning that value. Similarly, we can calculate the number of nodes. So this would be the number of nodes in a subtree starting with the current node. So if we called this with 4, number of nodes would return 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we called it with 1, number of nodes would return 6. If we called it with 2, number of nodes would return 2, for example. Okay, so we calculate this by saying if the left child is not null, so if there is a left child, find out how many nodes it has. If there's a right child, find out how many nodes it has, and then just return 1 plus the number of nodes in the left subtree plus the number of nodes in the right subtree. So these two methods here give you an idea of kind of the common approach for working with binary trees. You're going to see a lot of recursion, right? Because you do a calculation for the current node, and then you do that same calculation for the left child or the left subtree and the right child or the right subtree. So similar approach, and you'll see that approach a lot. So that's pretty much it. That's the binary node class. Again, this class represents a node that has a left child and a right child. That node might have a left child and a right child and so on until you get down to the leaves, which have no children at all. And it also provides methods for getting the height and getting the full number of nodes that are at that node or below. So we use this class along with the binary tree class to create trees. So again, the node represents just an individual node. The tree represents a collection of nodes. And the instance data that we use to represent this tree is just the root, right? Because each individual node keeps track of its children. So the root keeps track of its 2 children. Each one of those childs keeps track of its children, and so on and so forth. So for the whole tree, the only thing that I need to keep track of to be able to identify a tree is the root. And then through the root, I can get to all the children and the children's children and so on and so on. I don't need to keep track of all that. I just need to keep track of the root, this one here. And then I can use the pointers of left and right to find my way down the tree however I need. Okay, so my instance data is just one node, the root of the tree. Now in setting up my tree, I can set up my tree to just have a null root. So this would be an empty tree. There's nothing in it. I can set up my tree to have just a root. So I just send in the data that's going to be stored in that root. And then I create a binary node with that data. And recall from the constructor that just takes in data of binary node, this is going to create a node with data, but null left and right children. Sorry. So basically no left child, no right child. And then the third way to create a tree is to specify the data that's going to go in the root and then send in a whole tree that's going to be the left and the right subtrees. Now these whole trees could consist of just single nodes, or they could consist of full trees. So in our case, if I'm creating a tree with 4 as the root, I would send in this whole tree as the left tree and this whole tree as the right tree. On the other hand, if I was creating a tree with 7 as the root, I would just send in this tree as the left, this tree of 1 node, and this tree as the right, this tree of 1 node. So those are the 3 ways I can set up my tree, with no data at all, with just a root but no children, and with a root and 2 subtrees. Now again, there are other implementations. This is just the one that we'll be looking at. Now inside this third constructor, we invoke a method called private set tree, which we're going to look at in a moment. We also have 2 public set tree methods, and these allow you to set the data that should be at the root of your tree. Basically setting the root with no, and then the root will now again have no children, or allowing you to set the tree to have a root and the 2 interfaces. So these set methods are very similar to the constructors, but it just allows you to, instead of having to invoke the constructor and create a whole new tree, it allows you to basically swap out the contents of the tree. And the real meat of this class comes in the private set tree method. So in private set tree, we have a root, a left tree, and a right tree. So you'll see that here, where we pass that left and right tree in that were sent as parameters. So in the private set tree method, what we do is we create a new root node, a new binary node with no children. And then we just look at this left tree and we say if it's not null and if there's something in it, right? So it's not null and it's also not empty. We set the left child of the root to be the root of the left tree. So this would basically be saying set the left child of 4 to be the root of this whole subtree, which is 1. And then we do a similar thing for the right. We say if there's something there in the right tree and that tree isn't empty, then we want to set the right child of the root to be the root of the right tree. So again, the right child of 4 is going to be the root of this tree, which is 3. Now this little part here about seeing if they're the same trees, if you pass in the same tree as a left and right tree, what this will do is it'll just make a copy so that you have unique nodes being used on each side of your tree. And then this just releases or deallocates those parameters so that, again, we don't have multiple references pointing to the same tree, but we're keeping unique copies. Some other getters and setters. So we have a node to get the root data out, checking first to see if it's null, and if not, then getting the data. Checking to see whether the tree is empty, which will happen if the root is null. Clearing the tree, so setting the root to null. Setting the data of the root. Setting the whole root node. Getting the whole root node. To get the height of a tree, the height of a tree is just going to be the height of the root, right? That's the same thing. Height of a tree is the height of the root. Similarly, the number of nodes in a tree is just going to be the number of nodes that are at or below the root node. So we just return the number of nodes invoked on root. So those are our basic kind of getters and setters and constructors for the binary tree class. So make sure you understand how we build these trees. And we essentially do it by specifying subtrees and then kind of linking them up together. So I'm going to show you an example of that before moving on to the last part of the binary tree class, which has to do with the traversals. So here we have a tree tester class, and this is the code that we could use to build this tree here. So essentially what we do is I first create all of my interior nodes, and I'm just creating them as empty nodes. I'm not specifying the data, and there is no way to specify the children when I create my node. Remember that the only ways to create I'm not yet using the constructor that allows us to specify the children. I'm just using this constructor here where we basically just create an empty node. And I do that for my interior nodes. So those are the nodes that are not the root and are not the leaves. So that would be the 1, 7, 9, 2, and 3 nodes, those 5 nodes here. Those are my interior nodes. So I create them here, and I've just called them node 1, 3, 7, 9, 2. So those are my interior nodes. Then I create my leaves, and I'm using the second constructor where I actually specify the data to create my leaf nodes. So I create my leaf nodes for my leaves, which are 6, 11, 14, 5, and 12. So here I create my leaf nodes. Then I create my root. Okay, and my root I'm creating again without the data. Now you'll note that to create these nodes, I'm actually creating them as binary trees. So I'm not actually creating just directly a node, but I'm creating a tree that consists of a single node. Or in these cases, a tree that consists of no nodes. It's just empty for the moment. But when I create my leaves, I'm actually not creating binary nodes. Again, I'm creating binary trees that are singleton trees. So they're trees that consist of just one node. And then what I do is I build my tree from the bottom up. Okay, so here I say, well, take my node 7 tree, which remember didn't have any data in it yet, and set the tree. So the first parameter of set tree is the data that's going to go in the root of this tree. So here I'm looking at just this little tree here. So I set the root data to be 7, and then I set the left subchild to be the node 6 tree, which is the singleton tree, and I set the right subchild to be node 11 tree, which is this singleton tree. So now this little tree is built, and it's called node 7. Then I set node 9, and I call the set tree method to set the data of the root of this little subtree to be 9. I set the left subtree to be the node 14 tree, and I set the right subtree to be null because there is no right subchild. So now I've built two trees, node 7 and node 9. And now I can set the tree with the root of 1. So I call set tree on this tree here, the node 1 tree. And I say the data that goes at the root of that tree is 1. The left subtree, or the left child of that root, is this tree, the node 7 tree. And the right child is the node 9 tree. Then I do the same thing over on this side. I build the 2 tree by saying here's the data that goes in the root. Here's the tree that's the left child. Null is the tree that's the right child. This is just a leaf, so now I can build my 3 tree, saying 3 is the node that goes in the root of this tree. Sorry, 3 is the data that goes in the root of this tree. My left child is the tree whose root is 2, and my right child is the tree whose root is 12. And now I've built this tree. And then finally, I build up from the root. So I say, okay, now I'm going to set my whole number tree, the root to have the data 4, and the left child to be this tree, which is the node 1 tree, the right child to be this tree, which is the node 3 tree. Okay, so this series of code here shows you how you can build up a tree. Again, you create the interior nodes without any data. You create the leaves with your data. You create the root without any data. And then you build the tree up by moving bottom up, right? So you kind of build up in levels, creating these lower trees, and then using them as the right and left children of these higher nodes. So the last piece of this code is the traversals. So there's 2 bits of traversal code in here. One is just a traversal that will print the pre-order, post-order, or in-order traversal of that tree. So there's a method in-order traverse, pre-order traverse, and post-order traverse. And these methods will just do just that. They'll just print out the order. So it doesn't allow you to manipulate the nodes. It just allows you to print them out. So the in-order traverse is going to use a recursive. It's recursive. All 3 implementations are recursive. And here we see that if you invoke in-order traverse, we're going to call our private helper method, which requires 1 node to be sent. And so we'll send the root, because we're going to start at the root. And here we have our checking our base case, whether or not the node is null. So assuming the node isn't null, what we're going to do is first traverse the left child, then process, or in our case, just print the current node, the data of the current node, and then process the right child. So that's our in-order traversal. Process the left subtree, print the current node, process the right subtree. Similar thing here for pre-order. We invoke a private method which takes the root, and then we have our base case check. So assuming we're looking at a node that isn't null, first we process that node, print it out. Then we process the left child of that node. Then we process the right child of that node. Then the post order, again, calls the private helper method. First processes the left subtree, then processes the right subtree, then processes the current node by printing the data. So if we run this little part of it, we see that we get printed out our, here's the invoking. We can invoke numbertree.preorder traversal, in order, and post order. And we get our printout here, and you'll notice that matches what we looked at in the other videos for our pre, in, and post order traversals. Again, though, those methods just print the traversal. So if you actually wanted to get in and do something with each one of these nodes, those methods don't allow you to do it. They just allow you to print the tree in pre-order, in order, or post order. If you want to actually use that ordering to get at the elements in your tree, what you need to do is create an iterator. An iterator is something that's going to iterate or kind of cycle over all the nodes in your tree. And you can do that in, again, pre-order, in order, or post order. So to do that, we implement these methods, get in order, pre-order, or post order iterator. And there's also a level order iterator. We talk about level order in the textbook. So for all of these, they use either stacks or queues to create the ordering. And I'm just going to walk through the one for pre-order, and then I'm going to leave it to you to walk through the implementation of post-order and in-order, and post any questions you have about the post and in-order iterators on the discussion board. So for the pre-order, essentially what we do is this is a private class. This is an inner-nested class where we're creating this iterator. And what we do is we have a stack. Our iterator is going to be implemented using a stack, and it's going to be a stack of nodes. Okay, so when we create this iterator, what we do is we just push the root onto the stack. So we start off with the root on the stack. And as long as there is something on the stack, then our iterator has more to go through. So that's the has next method. Now the next method is what we use to actually get that next node. So what we do is we want to get the next node. So if there is something there on the stack, the next node to be processed is going to be the top of the stack. So we pop that off the stack. Then we get the two nodes, the left and the right child of whatever we just popped off the stack. And assuming that they're not null, we push them onto the stack. Right child first, then left child. And then what we return from that is just the data from the current node that we just popped. Okay. So again, if we want to do the pre-order iterator for 4, what would be happening is we would push 4 onto the stack. And then when we're ready to get the next element in the ordering, we pop 4 off, process it. Then we push on 3 and push on 1. Right? That means that 4 will be processed before its child nodes, which is what should happen for pre-order. Then we're ready for the next node. Right now, 1 will be at the top of the stack. So we pop it, push on 7 and 9. So 1 will be the next node process, which again is what should it be in the pre-order, and the 1 will be processed before the 7 or the 9. Then when we're ready to get the next node, we pop off 7, push on 6 and 11, right, and so forth and so forth. So using a stack is one way to implement the pre-order traversal. Now the way we would use this iterator, if I go back to my tester program, is I would say, hey, number tree, give me your pre-order iterator. Let's say, for example, we wanted to calculate the sum of all the numbers stored in our tree. To do that, we need to traverse the tree somehow. And so we need to use our iterator to do that. Now, if we're just calculating the sum, you could use any of the traversals, right? It doesn't matter if you use pre-order, in-order, or post-order, because the idea is we just want to visit all the nodes. We don't care what order we visit them in. For other tasks, obviously the order matters. But for just summing up, you can use any of the 3 orders. So what I would do is I would get that iterator, and then I would just say, as long as the iterator has more nodes to go through, get the next node. And in this case, I'm summing it up. So summing up the node, I should say, dot. Node is a bad word here. I'll get the node data. So the iterator, the next method actually returns the data portion of the node, not the node itself, but the data. Okay. So this is how I would use my iterator, and when I run this, you can see that it just sums it all up, all the elements in the tree. Okay, so there is your implementation. Now these classes, binary node, binary tree, and the one I just created, tree tester, they take a lot of other classes to run. So you'll need things like the binary node interface and the binary tree interface and the tree iterator interface, for example. So these classes need a lot of other classes to run, and I'll post all of them. But the main meat of what you'll be looking at is in binary node and binary tree. So you should have a good understanding of how these 2 classes work, and also how to use them to build trees and then traverse those trees using one of the iterators.